This video continues with application problems for exponentials. This first problem looks at population. The formula that's being used is something that looks similar to the PERT problem. The letters being used look a little bit different. The P, of course, looks at the population after calculation. P sub 0 is representing your initial population. Anytime you have that subscript 0, that's usually representing an initial value. The K, in this case, is representing your annual growth rate. And that usually is a percentage. This one in this case is found by B minus D. And T is representing the time in years. This may vary on how you find that depending on a particular problem. In our problem, for this example, we have the birth rate to be 0.0147 and a death rate of 0.0087, and we actually need to calculate our annual growth rate by calculating that B minus D to get 0.006, which is 0.6% for that growth rate. And also in this problem, our initial population is 281,421,906 people. We're looking at from the years 2000 to 2010. So our number of years will be 10 years. So putting this information into our formula, we're going to calculate the population to be 281,421,906 times E to the 0.006 for 10 years. And then we just put that information in our calculator and we find our population to be 298,824,064.8 to represent our population change. So that is just another sample of a variation of that formula, PERT formula, where it's used with a population situation. Another variation of a problem that's using our interest rate formula is to find how long does it take to double your money if you left it invested. All right, and our investment is at 6% interest, and it is $10,000 invested, and it is compounding continuously. Now, how it's compounded is also important because it also tells us which formula to look at. So if we are investing $10,000 initially, then how much will we have if it's going to double? Then we will have $20,000 when it doubles. So we know how much it is when we finish. We know our initial amount was $10,000, and then we have that E. The rate is 0.06, but we don't know the time, and so that's what we're trying to find this time. So in order to solve this, we're going to divide by our 10,000 on each side, and so we get 2 equals E to the 0.06 times T. Now, in order to get this variable out of that exponent, we've got to use our relationship that we know about exponents and logarithms. So we are going to apply natural log, since this is base E, to both sides of this equation. Now, when we do that, we're going to get a numerical value on the left side. And for accuracy's sake, I'm not going to find that numerical value yet. I'm just going to continue with natural log of 2. But on the right-hand side, because we have the natural log of E to some exponent, this will evaluate to be whatever that exponent is. So that is 0.06 t. The natural log of E will evaluate to be whatever that power is. And so that's how we get that exponent out of the top so that we can finish working that problem. And so now we divide each side by 0.06. And so the time will be the result of that. And so now we're going to actually calculate that value. The natural log of 2 divided by 0.06 is going to give us 11.55 for our answer, and that's going to represent our years, so we're going to change that to approximately 11.6 years in order for our investment to double. Another type of problem that might occur is a half-life, and this often occurs with radioactive material. And so we have a radioactive material called cesium-137, and it decays at a rate of 2.3% per year. We're going to use a formula that's similar to that PERT formula. A equals A sub 0 E to the negative K times T. Now, why do you think it's negative K? It's negative because it is a decay problem. So that's why it's going to be a negative rate. The A is representing the initial amount. So just like when it doubled and we had 2 there, since we're looking for half-life, we're going to let this be 1/2 equals, and we're going to drop the initial amount, E, changing that 2.3% to negative 0.023 T, and we're solving for T again. We're going to do the same principle that we did here. We're going to apply the natural log to both sides. And so we get natural log of 1/2 equals negative 0.023 times T, and we divide each side. by that negative 0.023 to find our time. And so again, we're going to calculate that. Natural log of 1/2 divided by negative 0.023, and we get 30.14, or as we round that, approximately 30 years to reach half-life.